This board's kind of high. But so I care more. Okay, so if you get the plot kind of wrong, that's okay. I'm going to show you how I draw plots. But if you get the plot kind of wrong, that's okay. What's the most important for me is so when you're doing Bode plots, what I want is table, starting game, and starting phase. If you get all these right and you drew the graph kind of wrong, that's okay. Like Bode plots, they're not the easiest to draw. So if you have these three things and you get the graph wrong, so what? You got everything else right. Bode plots are hard to draw. And to be honest, when you draw them by hand, they're never going to be 100% correct anyway because they're not straight lines, they're kind of curved. So yeah. So if you get all this right, I'm going to take very, very, very minimal points off if your Bode plot's just absolutely wrong. But, yeah. Okay. All right, so the first thing is draw an approximation of the Bode plots, magnitude and phase. Okay, so let's figure out what the initial gains are. So I want everyone to grab it. So this is actually going to be on the exam, so everyone just get out your calculators and let's all do this. So that when you have the exam tomorrow, you know how to do it. All right, so the solutions manual says normalize, but why do you need to do that when you can just put it in your calculator, right, and find the exact gains? What is going on? Okay, so let's look at so this is going to be based on your the Bode plot, the graph paper I gave you, right? The initial gains are based on the Bode plot graph paper. That's how you know where you start. So the lowest frequency on this particular graph paper that's given for this practice is in 10 to the negative 1, which is 0.1, right? So 0.1 rads per second, that's equivalent to our sine function in which the poles are 0.1 I, or j. We use j in joules. All right? So we're going to plug that in your calculator, it's I, right? So you're going to plug that into here, and that kind of tells you what your initial gains are. All right? So let's do that.
K is 1, right?
What?
K is 1 in this case?
Yeah. So let's plug it in. So, okay, in your calculator, there's no s, right? So it's just 1 over 0.1i times s plus 0.1i. I mean, it's so easy. Your calculator can just do this calculation so easily that it's like, why even do it anywhere else? Okay, so then this is s plus 0.1, or sorry, this is wrong. It's 2, right? 2 plus 0.1i, and then it's 3 plus 0.1i. So it's 1 over 0.1i, 2 plus 0.1i. I'm just plugging the 0.1i into all the s's. And if you plug that into your calculator, you get some complex number. So what you should do is this. The way to do it on your calculator would be, you get an answer, right? And then you do store into some variable, let's say x or a, whatever. No, we'll just make it m for magnitude. So store it into m. Does everyone know how to use the store function on their calculator?
Yeah.
Everyone know how to use the store function on the calculator? So you store whatever complex number you get on m, and then if you just do absolute value of m, you get some sort of number. Another thing you can do is just do abs of this, right? Absolute value of, or absolute value is the same as magnitude. 0.1 I, 2 plus 0.1 I. You can just do it all in one go. 3 plus 0.1 I. You can also do that. You can plug in, like this. Or you can store it into m and do absolute value of m. But either way.
Or just give a second answer.
Huh?
You can also use
As and then do second answer.
Sure, that's fine. That works too. Whatever way you want to do it, just make sure you get that. So anyway, what did you guys get? What number did you guys get?
2.49.
2.49 is wrong. 1.66 is correct. So yeah. So this is around 1.66. Is that what everyone got? If you didn't get that, let me know now. Who did not get 1.66? What?
I just have a question.
Yeah.
So do you always just choose 1 when you're doing this for K?
Okay,
Is there ever a time when we don't keep one?
well, the K, pretend the K is not even there. So it's, pretend it's, okay, so it's like this, right? You have a gain, you don't know what it is. And then you have, yeah, the gain is assumed to be 1. This is for unity gains. So Bode plots, all Bode plots are drawn based on unity gain. Unity gain means this is, yeah, it's 1. That's what a Bode plot is. It's assume that gain is 1. And then what that means is if gain is 1, the Bode plots are normalized, right? So that if you multiply the gains, then everything goes up accordingly. But yeah, gain is Bode plots are based on unity gains. So yeah, K is 1 for, so assumed to be 1 for Bode plots. That was correct. Anyway, so a problem is, all right, so we have a gain of this, but the problem is that's not in dB, so we gotta figure out what it is in dB. So converting this gain into dB is 20 times log of, remember, log base 10. In MATLAB you have to do log 10, but let's not worry about it. Okay, so 1.66666, whatever. And that gives you some sort of number. Someone tell me what that is. 4 point, yeah, something like that. 4.4 dB or 2. Doesn't, okay, 2. Right, so something like that. To be honest, if it's just relatively close, it's fine. Because on the graph, right, it's like you're not gonna be able to pinpoint that number anyway. So okay, we have our initial gains. Now let's start with our magnitude table. So the first part of our magnitude table is finding our initial gains. We found our initial gains. It's 1.66. So can anyone tell me? This is like a good type of word problem. So at a frequency of 1.66, not frequency of 1.66, a frequency of 0.1 radians per second, right? What is, and a sine wave looks like this, right? Let's say your input is this sine wave, right? And this has a frequency of 1.66. I don't care if you get the phase wrong, but can anyone tell me what the output would look like? So you have a frequency of 0.1, right? That's what we're doing. We're inputting a frequency of 0.1. That's what 0.1 I means, an input frequency of 0.1. Because if you have a 0.1 I pole, that creates a sinusoid or cosine. Sinusoid, same thing. A wave, it creates a wave. When you input a frequency, a wave of magnitude 1 and a frequency of 0.1 radians per second, what is the output going to look like? So this is what's going to happen. Since the gain is 1.66, that means you're going to get, we don't know what the phase is yet, right? Because I haven't drawn the phase table, but let's just say that there is no phase change, right? Then it's going to look like this. Oops, this one's dry. Let's do this. So the phase is not, no. So the phase is not right because we haven't done the phase table yet, but it's going to, the gains are going to be multiplied. That's what's happening. It says when you input a frequency of 0.1 radians per second, you're going to get, it's going to have the same frequency of 0.111, but the magnitude, right? The magnitude kind of shoots up. And as you can imagine, for like a second order system, a spring damper, mass problem, if you oscillate something at the natural frequency, right, what you get is some crazy overshoot, right? Fortunately, this is not a second order spring mass damper system, so it doesn't have that peak. But right now, so if this amplitude is 1, then this amplitude is 1.666. That's what it's saying. That's what it's saying about if you plug in a frequency of 0.1 and you get a gain of 1.66, it's saying that you're multiplying the amplitude of your output by that much. That's what a Bode plot shows you. Any questions on that? Okay. All right, so we have our initial gains of 4 point something. Okay, so let's start our frequency table. Or yeah, magnitude, yeah, our magnitude table, our gain table. All right, so we know the initial gain is 4.42. So let's start off with our initial frequency. So we have an initial frequency of 0.1. That's just where a graph starts at 0.1. All right. And then what else do we have? We have a pole, or sorry, yeah, we have something at 2, and we have something at 3. A frequency of 2, and we have a frequency of 3. All right, so what do we have going on in the system? We have 3 poles, right? We have a pole at 0, a pole at -2, and a pole at -3. All right, so if you have pole at the origin, a pole at the origin means what? What type of slope do we have? It's -20 dB per decade, right? It's throughout it affects the entire buddy plot. This is not drawing right. I only drew 0.1 here because that's where the graph starts. But anyway, so we have a pole at 0, and we know it's going to have effects of -20 dB per decade throughout the entire buddy plot. All right, it just starts from the beginning. No matter what this number was, it would still be -20 because it affects the entire thing. It's always a slope of -20 dB per decade.
Wait, how'd you figure that?
Because they have a pole at the origin. A pole at the origin means a slope of -20 dB per decade throughout the entire thing.
Okay.
All right. Okay, we have a pole at -2, so that doesn't start till 2 radians per second. So 0 here, but then it's -20 here, and then -20 here. And then you can guess what's going to happen for the next one. It's going to be 0, 0, -20. So the effect of the poles and zeros, as long as they're not at the origin, the effect of the non-origin zeros and poles start at basically, yeah, the absolute value of this. So -2 starts at 2. The effects starts at -2. So the gain plot is a lot easier because you don't have to worry about starts. You don't have to worry about basically stops. The effect just carries on throughout the entire buddy plot. Just goes up forever. And then what we do is we add up the slopes. So this is -20, and then it's -40, and -60.
Hey, Andy,
Yeah.
could you explain like more closely how you like get each of those like the negative to like how you know? So like
The 20s.
yeah, the -20s. Like how do you know like the first one at -2 is 0, but the second one is -20 and like.
Wait, how do I know this one, these
Like
two are
that,
0?
like, how do you know like that, like the pole at -2, like how do you know the first one's 0, but then at 2?
Oh, okay. So remember this: the effects of a pole on the phase plot or like the magnitude plot, right, doesn't happen until this frequency. It only happens. So the effects of this pole. So if the effect of the poles don't happen until basically this value.
So that doesn't get affected until you reach the actual.
Yeah.
number that's at.
So basically, before
It's
2 and 3,
corresponding.
these don't even exist. Pretend they don't even exist.
Okay.
So the effect of these poles don't even happen until they reach a certain frequency. You just don't see a response from them until they reach a certain frequency.
It's always -20, right?
It's always -20
Yeah,
every
you-
single time.
So it'll kind of be in that pattern regardless.
Yeah.
I have a quick
Okay.
question.
Yeah.
What happens if we throw in a 0 as long as it gets thrown off?
What?
If we hit a 0,
A 0? Okay. You want to do 0? Should I erase this and do 0? This is the answer for the practice, but we can do 0 right now. I can do a separate one. So let me write down what the gain is. So initial gain. Let's do every single scenario. So initial gain is 4.4 dB. All right, so this is the actual problem. I'll erase everything else. Let's just do some practice. Oops. So every single scenario, let's just do right now. So let's come up with a transfer function. With some gain, doesn't matter. But all right, so a couple scenarios we can have. We can have a 0 at the origin, right? We could have one that's not at the origin, so s plus, I don't know, give me a number. 4. All right. And then we can have a pole at the origin. Problem is, these cancel out, so it wouldn't matter. How about I just do a pole, or 0,
okay.
and not worry about that. And then let's do s plus, I don't know, 3, and s plus 5. Something like that. All right, let's do the exact same thing again. So we have, in this case, let's pretend our graph starts at 0.1, and then we're going to have 3, and 4, and 5. All right. So we have a 0 at 0. We have a pole at 3. We have a 0 at 4. Right, these are negative, sorry. And then we have a pole at -5. And these represent when you're going to start seeing the effects of the poles and zeros. For a 0, right, it's the opposite of a pole at the origin, right? A 0 at the origin means +20 throughout the entire thing. And obviously the poles do the same thing, so you don't see the effect of the pole until 3, so -20, 20, 20. And if you got a 0 at -4, that's also going to add 20, right? So 0, 0, +20, +20. And then a pole at -5, you don't see the effect till 5 radians per second, and then you're going to add, subtract 20. So let's see, if we added all these up, we have a slope of +20, then 0, then +20, then 0. All right, any questions on any other scenarios?
Let me copy that real quick.
Okay.
So there's a question.
Yeah, yeah.
Would you ever do this where we have, if there was like an S plus 3 squared in the bottom?
An S plus 3 squared? Sure. Okay, that's one scenario I didn't talk about, right?
What?
A squared pole.
Oh.
What happens when something is squared?
Is it just double the value?
Yeah, you're just adding double the slope.
So it'll be -40?
Yeah, it'll be 40 now. Yeah.
What if there was like, what if there was a pole and a 0 at the same location? Or is that like not even?
They cancel out.
They
They
cancel
Yeah,
out.
okay,
Okay.
yeah.
Oh, yeah, duh. Sorry, my bad. My bad,
That's
yeah.
why I said I didn't want to do a 0
Yeah,
and pole at the same place, because it's like, no, that doesn't make sense. Yeah.
And it works the same way with phases, right?
What?
It works the same way with phase?
Yeah.
Okay.
Yeah.
Cool.
Any other questions?
No.
No.
Because I was like, well, you can't have a 0 that's out there. Like, you can still draw them if you want. Well, no, the mathematically, it just cancels.
But I mean, if it was there, you did it out, it would just cancel the math.
Right.
All right. I'm going to try my very best to draw a log plot. See how this goes. Okay.
You could just sketch it. You don't have to do that.
Okay. All right.
It's up to you.
Let's see. So it's point 1. 1. 10. Okay. All right. Let's say our 0 is like around here. I hope that's relatively straight. And let's say, I don't know. This is 10, this is 20. So. Let's see. Okay. All right. All right, so there's 2 tools that you're going to be using to draw these slopes. One is -20, or 2 definitions, I guess, per decade. Does anyone know what the other one is?
The octave one?
All right, how many per octave? 6.
Can we
Alright.
get away with not using the octave though?
Usually you can, but sometimes you just don't have enough space and you have to use that roll. And remember, octave does not mean going up by 8. It means doubling your frequency. The definition of an octave is a doubling of frequency. All right, so this is 0, 20, 40. And so far. Okay, so our initial gain was around, at 0.1 radians per second, our initial gains was around 4.4. So I'm just going to make a good guess and say 4.4 is around there. All right, and then it's going to go down by 20 dB per decade from 0.1 to 2. So let's just figure out where 2 is. So 2, let's say, is like right around. Yeah, let's say this is 2. Let's say that's 2. All right, so what you want to do is, so I'm showing you, like, this isn't, don't stress out too much about this, but this is how I do it. So I look at, so it's 20 dB per decade, right? We start at 0.1. We start at 0.1, right? So what is 1 decade? 1 decade from 0.1 is 1, it's 10 times. So it'll be over here. So what I want to do is, like, I want to get a look, so you just like a slip of paper or a ruler and kind of draw another point at 1 that's around 20 decades lower. So it's on 0.4. So what's 0.4, or sorry, what's 4.4 minus 20?
Negative 16.
All right, so let's say negative 16 is like around, I don't know, like here-ish, right? Let's say negative 16 is around there. So what I want to do is take this point and draw another point here, and then make a line that extends all the way to 2. So we know that this is exactly 1 decade. We know that the drop is exactly negative 20. So we draw a line that goes through, and we know that it stops at 2, because at 2, the slope becomes negative 40. So then we do that. We keep going and going and going. It's probably way off because my graph is crap. But, oh, it's actually not bad. That's actually pretty close to what it is. Great. So what I did was I made this point and this point as reference points, because I know that this is exactly a negative 20 dB drop, and this is exactly a 10-fold increase in frequency, which is a decade. So I know that this slope is correct because I use the reference of 20 dB and then 1 decade, because like the lines are correct. The only thing that might be slightly off, is that this point right here might not exactly be 15.6. That's okay. Right? It's going to be, this is fine. So our initial starting point based on this was 4.4. We drew a dot there as a reference point, and drew another dot here because this indicates negative 20 dB per decade. I went 1 decade across, and then, yeah. Okay. So the next step is looking at our next slope. It's negative 40. So from 2 to 3, so it's going to be negative 40. So 3, it's like, goes like this. It's log, so the width gets shorter. But anyway, so all right, let's say that our reference point now is here. This is where we ended up on our frequency of 2. So we extended the line, and when we hit a frequency of 2, we stopped at around here. Okay, so the next slope is negative 40 dB per decade. All right. So this is the tricky part, or not that tricky, but okay. So this is 10.
So wouldn't you just draw it to 20?
Yeah. So this is 20. Sorry. This is 30. All right. So we're gonna drop. So right now we're at negative 20. What's a 40 dB? So our slope is negative 40. So we have to drop by 40 dB. So negative 20, so we've got to go to 60, right? So 1 decade from here is here, right? So we're starting at 2. A decade increase is 20. So 2 times 10 is 20, and we're going down by 40 because the slope is negative 40. So from negative 20 to 60, so we're going to end up right around here, right? And so you draw your line that extends from here to here. Oh gosh, I think that's right. Okay, so let's say you drew the entire line, and you did it in pencil because you're not an idiot. So, because this only applies from 2 to 3, right? 2 to 3, you erase everything beyond 3. So what I did is I drew a reference point here and connected the lines because that ensures that I have the correct slope. I went down by 40 dB and I went across a decade. So that ensures I have the correct slope, and I draw the line across. Once I'm done with that, I erase everything I don't need. I don't need anything after 3, right? Because after 3, it changes to a different slope. So from 2 to 3, we have the correct slope, but anything beyond that, it doesn't matter. So we draw our next reference point like that. Any questions? You look like no questions. Anyone good? Everyone good? All right. So the last one, we have a slope of negative 60 dB per decade. So it's literally the exact same thing. Someone pretend they know what number this is. What do you think that is? All right, now subtract 60 from that. What? So negative 90, sure. So that'd be like around here, right? So here, and then a decade increase would be like over here, right?
Yes.
All right. So fortunately, everything ends. This is our very last polar 0, and so all we need to do is just draw. Oops, I messed that up completely. All we need to do is just draw that line forever, and we're done. That's it. All right. I hope that was informative. Sorry, yeah, I would have liked to have done this more in class, but it's just so time-consuming because I got to draw like, I don't know.
Well, you never did the minus 60, did you?
Yeah, that's what I just did right now.
Oh, okay.
Right. So this is a 10 dB, or 10 decades, or sorry, not 10 decades, but it's 1 decade, right? This is 1 decade, and then I dropped by 60, right? This is a drop in 60, and it's an increase in 1 decade.
Okay.
Right? Does that make sense? Yeah. So
Yeah.
that's what it just. And since that's the final slope, that negative 60 just goes on forever. Okay. No, I gotta do a face plot now. Okay.
Is everyone okay if he doesn't draw the plot?
Just the table?
Yeah.
You guys are good with plots now?
Yeah.
Okay. Yeah. No. Thank you. Thank you so much.
Are we gonna be designing compensators for the Bode plots like?
No, never. No. No lag and no lead compensators on this exam.
Okay.
Or no, that's not true. No lag and lead compensators based on frequency response.
Right.
Yeah,
like,
Bode
like in
plots.
chapter.
Yeah, no Bode plot stuff that involved. You will have to do like phase margin, right? And
Oh, yeah.
gain margin.
Okay.
Phase margin, gain margin. Remember that like extra credit things you guys took? That will be on the exam. But in terms of designing a lag and lead compensator for a frequency suite, no, you don't have to. That would take too long. That will be on the final though. They'll be guaranteed on the final. But not on this midterm.
So that's that worksheet where we have to find beta and T.
No, we don't. No, don't worry about that yet. Worry about that for the final. All right. So, can anyone tell me what the initial phase is?
-90.
How'd you know that?
Because there's a pole of the origin.
That is correct. So if there was a pole, or sorry, if there's a 0 at the origin, what would be the initial phase? Yeah. Oh, sorry. Okay. So all right. So if there was so if there's a pole at the origin, your initial angle is, as you said, -90, right? And if there's a 0 at the origin, then your initial angle is 90 degrees, positive 90 degrees. So since we have this, initial phase is equal to It's so weird that like we're using like radians and like frequent like degrees just like randomly throughout like the course. It's like you don't say it. Yeah. Question.
No.
Yeah.
Yeah. What if there was no s in the denominator, so it was just s plus 2 and s plus 3? Where would you start there?
If there's nothing at the origin, is what you're saying, right? Then you just start 0.
Oh. Is that
Yeah. If you don't have anything, you start at 0. If you have so it starts at 0 if you have no pole, nothing, but if you have no poles or 0 at the origin, you start at 0. If you have a pole at the origin, it's -90. If it was 0 at the origin, it's positive 90. All right, so pole at the origin, so it's negative 90. Just getting in the habit of like memorizing this. Remember, like just in general, poles are negatives, and then right, zeros are positives. Even when you were summing up the angles, right, in the root locus, zeros were positive, poles were negative. Right, so this is just the general rule. When you think zeros, think adding. When you think poles, think subtracting. Okay? Poles minus zeros plus. There's probably some sort of pneumatic device for that that I don't know. But yeah, okay. All right, so let's look at, so we don't need to look at this yet. All we need to do is look at the non-zero poles and zeros. So yeah, the non-zeros, poles and zeros. Yeah. So this is one at the origin. We don't really worry about that right now. We already know the contribution of this origin pole. It's negative 90. It starts at negative 90. But let's look at the other ones. So this is very, very important. The effects on the phase. Oh, can anyone tell me what I mean by phase? What is this phase in terms of, okay, when you're given a Bode phase plot, what does that plot show you? What does a Bode phase diagram show you? Okay, you know what? I'm definitely going to put this on the exam. All right? I'm going to have to explain, you're going to have to explain to me in your own words what a Bode plot is actually showing you and what a root locus plot is actually showing you. If you don't know what those are, if they're just like random graphs to you, then what are we doing here? You have to know what those actually are. So know what actually, so okay, first of all, root locus. What in the world is that showing you? What is that a graph of? That's not good.
Oh, I might know.
Okay.
Isn't it how the poles change as you increase gain?
Okay, so the complete correct definition is, what it shows you are the x's and zeros on the plot, or the x's and o's on the plot are your open loop gains. But what the lines show you, that as your gains increase from 0 to infinity, how your closed loop poles change. The location of your closed loop poles. So as your gains increase, it shows you basically how your closed loop poles change. So if you had a root locus like before that looked like this, like that, like that. So these are arrows. So as your gains are increasing, right? As k goes up from 0 to infinity, remember, a root locus plot does not show you the gain or the poles for negative gains. It just doesn't do that. But anyway, so as gains go up, then your poles move out.
That shows how open loop poles change as a gain.
No. The x's, right? These black x's, those are your open loop poles, right? The lines on a root locus are your closed loop poles. That's what they represent. Those lines represent, for different values of gains, what your closed loop poles are. That is what a root locus plot is. Basically, it's a graph of gains versus closed loop poles. That's what it is. The x's and o's, the black x's and o's on your root locus plot on MATLAB or whatever, those represent your open loop poles and zeros. All right, those are your open loop poles and zeros.
So root locus show that.
And so the lines in the root locus, right? The actual lines represents how your closed loop poles change as your gains increase. That's what those lines represent. And that's why you'll see different colors, because you have to know the trajectory of the different poles. If they were all one color, they'd be like, oh, which one is doing what, right? That's why they're different colors. Like you'll see like in MATLAB, you'll see like maybe this shows red and this shows blue or something. But it shows you that this pole starts here, goes towards here, and then goes up like that.
What about Bode?
Bode? What is a Bode plot? Okay, yeah, sorry, that was the first question, right?
That was the first one.
So a Bode plot basically is showing your gain and your phase for a frequency sweep. So whatever the x-axis is, the range is. So a frequency from whatever, like 0.1 to whatever 100. So basically for a range of frequencies, a range of input frequencies. So the input is like sine of x, something like that, or sine of t. So you have a sinusoidal input, right, with a magnitude of 1. And you're sweeping it through a range of frequencies. So there's like I don't know. there's a range of frequencies that you're increasing it by. So you start at a really low frequency and then you go really, really fast. Basically, through those range of frequencies, it shows you, if you have a certain input, what the output magnitude is going to be, what the output, yeah, sorry, you have a question? No? Okay, so for a range of frequencies, it shows you what the output is going to be, the magnitude of the output, if the input is 1. The input has a magnitude of 1, what is the magnitude of the output going to be? So if you have a gain of like, I don't know, like 0, right? A gain of 0 dB, and that means you had no increase in gains. It's still 1. A 0 dB gain means just you stay the same. But if you increase, right, that means like if your gain was like, I don't know, like 2.2, then that means your amplitude is going to be multiplied by 2.2. In terms of dB, I don't know, it's 20 log this, right? Whatever that is. But it basically shows you got to convert whatever dB you have back into gains to figure out what the amplitude is. But it basically shows you what the amplitude is going to be. And for a lot of problems we did, what you saw was an attenuation in dB, right? So that means eventually no information gets transmitted. Basically, at a certain frequency, when you go really, really fast, right? That means you're going to see like very little. So like you're shaking like this, right? But the thing at the end is just going to be like this. It's going to barely move because that's what you saw in the last Bode plot. You saw an insane attenuation, and like with really, really high frequencies, nothing's going to happen at all. You're just shaking it so fast that like the system doesn't allow any information to be transmitted to the actual mass, right? It's just so, you saw the video, right? Where you shook it really fast. Yeah, so that's what it's saying. Basically, it's showing the magnitude of your output as frequency changes. And what the phase is no matter what, the frequency, this is very important, the frequency of your input and the frequency of your output are always the same. The things that are different are your magnitude and your phase. So what I mean by phase is how offset the input and output are. So like the input is this and the output is this. That's your phase. Is how offset it is. That's what a phase is. So that's what a Bode plot is. It shows you your phase offset and your increase in gains for a frequency sweep or a range of frequencies. And I'm definitely going to put that on because it's really important that you know what you're actually doing, what we're actually working with, not just randomly doing math problems.
Sorry, can you repeat what you said, that it was a phase, like it shows the phase offset for the phase diagram and the magnitude diagram?
So the magnitude diagram shows you your increase or in amplitude or your factor increase in amplitude or decrease in amplitude, right? If it's like a decimal number, right, then it's like a decrease.
Okay.
So it basically shows you your change in amplitude of your output. Your phase diagram shows you the offset of the phase or the angle, yeah, between your input and your output.
Can we just say that it shows the gain in the phase for a frequency sweep? Or is that not specific enough?
Be a little bit more specific than that. I would like you to use the word offset if you can.
Okay.
I'd probably give you the points though.
Okay.
Okay, let's do the table. Everyone good on what you're actually doing when you're drawing root locus and Bode plots? Everyone know what's happening now? Kind of, maybe? Sure.
So it's like no sine omega t plus.
Okay, I'm gonna build it. Okay, what am I doing? Okay, so phase plots are a little bit more difficult than magnitude plots because they have starts and stop points and they're kind of funky where they start and stop. So these rules are just based on some guy that's like, yeah, these are good approximations. So there's no like real clear derivation of like why he chose these, but it's just like close. So he just chose these numbers. Anyway, so okay. So we don't worry about the poles and zeros at the origin because we know what they have starting effects. They affect the start of the system. So we don't care about that. All we care about is the non-zero poles and zeros. So, or non-origin poles and zeros. So we have 2 and 3. So what happens is the frequency, the effect of the phase is affected basically 1 decade below this and 1 decade above this. So that means whatever numbers you have here, you divide it by 10 and multiply 10, and all those frequencies should appear on your phase table. All these non-origin poles and zeros, whatever numbers you have on there, you should have that number divided by 10 and that number multiplied by 10. So basically, if you have 2, you should have 0.2 and you should have 20. If you have 3, you should have 0.3 and you should have 30. And make sure you draw those in the correct order. So it's 0.2, 0.3, 20, 30. So, yeah. All right, so we don't worry about the origin stuff, so we just do pole at -2, pole at -3. Okay, so the -2, the effect of the -2 pole starts at 0.2 because you divide it by 10 and it stops at 20. So it's -45 dB per decade, so that's the magic number. There's no other second magic number, this is it. So if you can't use this, then that sucks. Okay.
Wait, you said it was -90 to start.
We're not doing starting stoppings, we're doing slopes.
Yeah, it
This,
starts at
this is a starting point, not a slope. Remember how like the 4.4, remember the 4.4 dB
Yeah, yeah, yeah.
was an initial starting point? Like that, this is an initial starting point.
Okay.
Okay.
What's happening from point 1 to point 2? Is it just a flat line?
That's correct. No. Well, yeah, it's 90. It's negative. Starts at negative.
but
Yeah,
it's just like-
yeah, flat. It's flat. So anything before. Okay, yeah, that's a very good question. Anything. So that's not like very intuitive. So you're right. Anything before 0.2 is a 0 slope. Anything before 0.2 has a 0 slope of 0. Maybe I should draw the plot. Anyway, so is there any effects by okay, so it stops here, right? So it goes from -45 to -45, -45. From here to here is -45, but at 20, it stops at 20. So it starts at 0.2 and it stops at 20. So starts at 0.2, stops at 20. And it's 0 for the rest of that. Now we go to pole at -3. So it doesn't have any effect until it's 10, or 1 decade below 3, which is 0.3. So it's -45, -45, and then it stops at a decade above that. And so the slope is -45. You know what? I won't draw the plot. I'll draw you the piecewise function. Or not draw you, but I'll write the piecewise function. -90. 0. So how to interpret this graph? So for -infinity to 0.2, slope equals 0. For 0.2 to 20, let's see, no, 0.2 to 0.3, that's incorrect. So 0.2 to 0.3, slope is equal to -45. And then for 0.3 to 20, slope is equal to -90. And then 30 to infinity, slope is equal to 0. Yeah.
I get the why do -45 at 0.2 and 0.3, and then so I just don't get the 20 and 30. That's what I don't really understand.
Wait, so you got this and this?
Yeah.
You don't get this?
Yeah.
0 plus -45 is 0.
Well, no, I get that.
Okay.
But like, why is it -45 at 20?
At 20?
Yeah, at pole -30.
Because you still, at -20, you still have an effect from 0.3, but the effect of, sorry, yeah, you still have an effect from pole at 2, but you stop the effect at pole 2, but you start the effect at pole 3. So the effect of the pole has starting and stopping points. Eventually, it doesn't affect the plot anymore. That's why it's -45.
So, Andy,
Yeah.
so basically the effect of the pole is from 1 decade below to 1 decade above.
Yeah, that's correct.
Right?
So, okay, so if your pole is at here, the effect happens from 0.2 to 20.
Yeah, I think that was Ian's question.
Okay.
Does that help?
So you see how?
Yeah.
Oh, he's explaining.
Yeah.
Yeah, 20 to 30.
Whoops. And then 30 to infinity, slope 0. So eventually all Bode plots, it's not slop. Okay, so eventually all Bode plots, right, they kind of plateau, right, at the ends. As long as you have enough graph paper to show that. Okay, any questions on the slopes? I can draw a mock Bode plot right now just so people get an idea what's happening. It's going to be very, very terse and crappy. So let's say this is negative 90. All right, from 0.1 to 0.2, it's just flat, right? And then you have from 0.2 to 0.3, like a slope of negative 45 or something like that. And then from then on, it's from 0.2 to 30, that's a bit larger, so that's like negative 90, something like that. And then another slope, again, of like 45, and then just like that. That was bad, but that's kind of how it looks. So, yeah. 0, negative 45, negative 90, negative 45, and 0. Slopes. Okay. Why can't I do that? Okay. I can't draw that. Okay. So, any questions on drawing the Bode plots? Yeah.
Is there a degrees per octave equivalent of 45?
No, I'm sorry,
That's
man.
not a nice number.
No. It's not as nice as 6. 6 is like very, very, very close. But if this doesn't work out for you, just let me know.
But it should work, yeah.
Okay.
The exam.
What else are we doing? I think that's all I really wanted to cover. So for parts, so you guys got
What about
a really
B&C?
good hint in that you know what the word problem is going to be. Yeah. Here's the problem. In order to finish this problem, right, you have to have very accurate, or not very accurate, but you have to have relatively close Bode plots to work with. So can everyone log onto a computer? How about that?
Oh.
Because the problem is, if I draw this and I try to do the problem for you, it's going to be off, because my Bode plot's going to be so crappy.
I could just yell MATLAB
Oh,
numbers But
Okay.
we should be able to do it by hand.
You should,
tomorrow.
okay, so I didn't have graph paper, right? I didn't have graph paper, so my Bode plots were crap. Once you draw yours like this, you're going to be able to figure out your gain and phase margins very easily.
Oh, okay.
Yeah.
Do you just want to do it in MATLAB?
MATLAB? Maybe, sure.
That way we can do the rest.
Does anyone know how I use this projector? I've never done this before.
Well, I was just gonna say you could just.
Discord? I do not have that. I don't have that input. I don't have that video. Okay.
It's on.
Does anybody want to be a volunteer?
The solution has online, it's really straightforward.
What? I don't know if
Remember, did you get the drawing out?
I don't know if that works.
And start measuring stuff?